If you take away one concept from neurophysiology, it will probably be the action potential. The action potential is at least discussed on some level, basically anytime anyone dives even a little bit into neurophysiology. The action potential is the mechanism by which electrical conduction happens across the length of a single neuron. So when we think about electricity moving through a wire, you know that electricity moves really fast, and the electricity is actually a series of electrons that are kind of bumping their way across a wire, but it's a very rapid conduction. And in the same way, we're going to see some changes in the membrane potential that are also very rapid and very predictable. And they represent our cell's version of electricity moving along a wire. But instead of moving along a wire, they're moving along the length of a cell, which for a neuron can actually be quite long. So action potentials occur in the axon of a particular neuron. And action potentials have the word action in them, which is a converse or an antonym to the idea of resting. So we've so far looked at resting membrane potentials, where if leak channels and the sodium-potassium pump are the only thing at play, the membrane potential will be at rest or at minus 70 millivolts. But now we're going to start opening voltage-sensitive gated channels. And for the neuron, there are two voltage-sensitive gated channels that play a role in the action potential, one for sodium and one for potassium. And when they open, they allow that ion to move down its chemical gradient and therefore cause a pretty substantial deviation in the membrane potential. So action potentials can occur in any cell that is excitable. So we actually have that phrase as excitable, which basically means that it can use electrical propagations, action potentials, as a way of rapidly communicating across a cell and maybe to a neighboring cell. Action potentials vary a little bit depending on if you're in a neuron, a skeletal muscle fiber, which is also excitable, or even cardiac tissue, which is also excitable. But all action potentials have this in common. They all have a rapid depolarization and a rapid repolarization. For a neuron, the tracing of the action potential is going to look like this. Now, I don't want you to write anything down yet. I simply just want you to look at the red line and confirm that in fact there is a rapid depolarization followed by a rapid repolarization. And by rapid, look at how short that time frame is. Those are not seconds, those are milliseconds. 1 millisecond is 1/1000th of a second. So an action potential takes course over the span of 2 to 4 milliseconds, which is incredibly fast. Now we are basically going to diagram out what you see here in this image, but I don't want to just have you stare at this. I want you to write it down yourself and go through the story as I tell it. So what I would like you to do instead is take a moment to pause the video and copy the empty graph that you see here. Give yourself at least half a page to copy this graph. So, we are going to do a series of events on the right, much like you saw in the previous graph. And then we're going to use the center and the left part to actually demonstrate the tracing of the action potential. So our story starts with our membrane potential at rest. Now, something is happening, and we do not know what is happening, but something is happening to cause our membrane potential to actually start to depolarize a little bit. So it's so strange that we actually start our story with something that I can't even really talk about yet. But this is a big question mark. We don't know what is causing this. We just know that something is bringing that membrane potential up. Notice that I have minus 55 marked here. There's a reason for that. It turns out that minus 55 is a threshold that is required to open the voltage-sensitive gated channels. So, in particular, the voltage-sensitive sodium gated channel will open rapidly in response to the membrane potential reaching or crossing the -55 threshold. So once the membrane potential, for reasons unknown, crosses that -55 threshold, that is going to be our first event where a large swath of voltage-sensitive sodium gates are going to open. And there are a lot of voltage-sensitive sodium gates. So this is not leak channels where there are very few of those. There are a lot of voltage-sensitive sodium gates. So many that sodium basically can reach its electrochemical equilibrium. Do you guys remember what the electrochemical equilibrium was for sodium? It's at +30. So what that is going to do is cause this membrane potential to rapidly reach +30. Okay, let me go ahead and write our step 1 down. Okay, I'm going to use the rapid depolarization as my step number 2. This is where sodium rapidly comes into the cell, so we'll call that influx into the cell, and that's what causes this rapid depolarization. Now, once I reach my +30 mark, which happens about half a second later, two things are kind of going to happen at the same time. So first of all, my sodium gates are going to close. So that's definitely going to be one event. Now, as my sodium gates close, if nothing else were to happen, what do you think my membrane potential would do? And I don't want you to write this down because I'm simply just trying to demonstrate what would happen if that was it. That was the end of our story. Voltage-sensitive sodium gates close and what? Well, based on our previous lecture, we would kind of expect this membrane potential to eventually drift back down to the resting standpoint of -70 millivolts, but it would probably take a while. And we don't have a while. So instead, we're going to open up another voltage-sensitive gate that will help us rapidly repolarize this, and that is going to be our potassium gate. The voltage-sensitive potassium gate is also sensitive to the -55 threshold, or the depolarization, but it's slower to open. So it doesn't open right away like sodium does. Sodium opens rapidly, and potassium kind of takes its sweet time and decides that it's going to open a little bit later. So as the sodium gates are closing, the potassium gates are actually starting to open up. So these things happen around the same time. So we'll go ahead and just make this number 3. I have it as a very precise point, but in reality, it's more of a gradient. The sodium gates don't all open at exactly the same time. They open mostly at the same time and they close mostly around the same time. And as the sodium gates are closing, the potassium gates are starting to open. And by the 1 millisecond mark, you might predict that all of the sodium gates have finally closed and all of the potassium gates have opened, but it is kind of like a little bit of a wave. So once the potassium-gated channels open, this allows potassium to move the way it wants. Well, potassium is going to want to exit the cell. And when potassium exits the cell, that is going to create a mass exodus of potassium, or a mass efflux of potassium. And it's going to move positive charge from the inside of the cell to the outside of the cell. And so what that's going to do is bring that membrane potential crashing back down. And in fact, so much potassium leaves that the membrane potential approaches potassium's electrochemical equilibrium, which you might recall from a previous lecture is actually -90. So we're going to see here kind of a rapid decrease, and we're actually going to go past that -70, closer to the -90. So we'll go ahead and put this as number 4. Now, once we pass the -70 mark, we're actually in hyperpolarization territory. So we would say that the massive K plus E flex causes rapid repolarization and even hyperpolarization. Now, it doesn't seem that we ever really get all the way down to -90 because the potassium gates begin to close. So we're going to mark this as our step 5 when the potassium gates close. So once the potassium gates close, there are no more open gated channels. And now the membrane potential is going to start drifting back towards its baseline or its default position, which is at -70. And again, that is going to be because of the sodium-potassium pump and the leak channels. So we'll use that as step 6. Okay, that is our basic story. So I'm now going to show you the book's description of this. And you'll notice that they use 9 steps, not 6. It really doesn't matter how many steps you use as long as you know the story in the correct order. And I am a strong advocate for telling these stories, these physiology stories, as if they were children's stories. Once upon a time, there was a membrane potential that was at -70 that started depolarizing for reasons unknown. And the sodium gate, which is super sensitive to that depolarization, rapidly opened once the depolarization reached -55, and then sodium was allowed to come in really fast, and then the membrane potential rapidly depolarized. You know, telling it like that, like it makes it so exciting that even like a 3rd grader could get into it. In fact, I'm kind of, I don't know if I'd say famous, but I would say that it's definitely one of my characteristics to tell stories like this. And I'll even tell them at different levels. So I'll say, you know, if it's a really complicated story, sometimes you can get lost in all the details. So I'll tell like the 3rd grade level story, and then like the high school reading level, and then finally we'll get to our college level reading. So at what level did I tell you that story? Probably the high school level, because we still have some more details that we need to add to our story. So it turns out that the sodium gated channel in particular is special because it is a double gated channel. So this worksheet is something that I usually hand out when I teach in-person classes. You can find it under Canvas, and it is called Mapping Action Potential Worksheet, and it looks something like this. It's a single PDF file or PowerPoint file, and you can see that it has the action potential diagram and then our 6 steps as we just described them. But up at the top here, we also have the ability to draw in the fact that sodium is a double gated channel, and there are 2 gates that behave a little bit differently. So when the voltage sensitive sodium gate is not doing anything, one of the gates is open. I'm going to go ahead and draw that like this, and then another one of the gates is closed. So what that means is that sodium, which is out here, still cannot come into the cell because the bottom gate blocks its passage through the plasma membrane. So in this configuration, even though the top gate is open, the bottom gate is closed, and therefore no sodium is allowed to pass. Once the membrane potential reaches -55, what we see is that bottom gate drops open. So now that bottom gate has swung open, sodium can move through. Now remember, it takes about half a millisecond later for the sodium gates to close. But what's really happening is that this top gate starts to shut on a timer. And so by the half a millisecond mark, the top gate has finally completely shut, but that bottom gate is still open. But once again, since one of the gates is closed, no sodium is allowed to move through. And then it takes another 1.5 milliseconds for the gates to basically rearrange themselves into their original configuration like so. Now in class, I usually mime this by using my arms as the two gates, and so I'll show you what I mean here. So what I just showed you acts out how these gated channels behave. Again, rapid opening when the bottom drops off, and then the top starts going until it closes, and then you spend another 1.5 milliseconds to reset it. So this double gated design is exclusive to sodium. Potassium is just a single gate. Potassium works like this. If this is the potassium gate, and it gets its voltage sensitive little jolt there, because it also opens in response to depolarization. It kind of takes its sweet time, waits about half a millisecond, and then goes, okay, I'll open. And then potassium is allowed to move out of the cell and cause that repolarization. Okay, that concludes our lecture on the action potential. Make sure you have a really solid understanding of the chain of events that cause the action potential, because we're going to build on that in our next lecture. I'll see you then.